mathematicians. In this video we're going to see about basics of continuous functions. Okay, so this is a series of lectures. In this first lecture we see what is continuous function, how to understand the definition of a continuous function. So today we just try to understand definition just by some drawing some diagrams, graph of the functions. Okay, so let's get started. So if you are new to my channel, please click the subscribe button and let's start. So I take two metric spaces M1 and M2 and I have a function f from the metric space M1 to M2 and I take a point A belongs to M1. Okay, so M1 is the domain of this function f. Then we say that the function f is continuous at this point A belongs to M1 if given an epsilon greater than 0, there exists delta greater than 0 such that distance between x comma a less than delta implies distance between f of x and f of a less than epsilon. Okay, so when we see the definition of, when we first see the definition of continuous functions, it is little difficult to understand. There is some epsilon, there is delta, and there is some inequalities, but once you understand what it means geometrically, then it is the very simplest concept to understand. So we go step by step. Okay, first, given epsilon greater than 0, that means that whatever epsilon it is given to you, there exists a delta greater than 0. That means that whatever epsilon is given to you, you can always find a delta such that satisfying this condition. Now, whatever epsilon greater than 0 means that for all epsilon greater than 0. Okay, so that is the first thing to observe. So even though we say given epsilon greater than 0, given epsilon greater than 0, that is actually means that for all epsilon greater than 0. Okay, so for every epsilon greater than 0, there exists a delta greater than 0 such that this condition should be satisfied. So now let's see what is this condition means. Distance between x comma a less than delta. Note that we are looking at d1. Okay, d1 is a metric in the metric space, which is metric space m1, which is the domain. Okay, so and a is a point in the domain. Now in m1, whenever there is a point x whose distance from a is less than delta, then if you look at the image of this point x, that should, that point f of x should stay within the epsilon distance of f of a. Okay, so let's see it again. For every epsilon greater than 0. Okay, note that we have fixed a point a. Okay, so we want to we want to check whether the function is continuous or not at this point a. Okay, so the function is continuous at this point a if for every epsilon greater than 0, you can always find a delta greater than 0. Whatever epsilon, you can find a delta such that whenever there is a x, okay, if there is a x such that distance between x comma a is less than delta, for every such x, distance between f of x and f of a should be less than epsilon. But again, this is a d2, so all these things are happening in m2. Okay, so now little bit it is, the reference is clear, but once we draw some diagram, it is going to be much easier. Okay, so to draw that, if it is a two arbitrary metric spaces, then we cannot visualize it. So to visualize it easily, I am going to assume that the function is from R2 to R2, two dimension, I mean to our two dimensional plane. Okay, R2 with a usual metric. Uh, so let's see. So let's see what this means. So I take a point A. So note that this is R2, okay, and this is another R2, and this is my domain. This plane is my domain, and this plane is my codomain. Okay. Now let's unravel the definition. So I fix this point A. Okay, so we assume that there is a function f from R2 to R2, and this is my point A at which I want to prove that this function f is continuous, and I assume that the function f maps A to this point f of A. Okay, so note that this is domain, this is codomain, so every point here will map to some points here. So I assume that this A is mapped to this point f of A. Okay, now what they are saying for every epsilon greater than 0. So, okay, so once you are given a epsilon greater than 0, what you have to do is you have to go to the codomain, because like epsilon comes in the right hand side of the implication. In the right hand side we are talking about the distance d2. Okay, d2 is a distance in codomain. Okay, now if you observe this inequality, it says that distance between x comma a less than delta. Okay, so what is the meaning of this? So if you, so distance between x comma a less than delta means that this point x belongs to B of a comma delta. Okay, ball with center at a of radius delta. Okay, so what is ball center at a of radius delta? Set of all x belongs to the metric space M1 such that distance between a comma x should be less than delta. This is the open ball center at a of radius delta. So this condition, distance between x comma a less than delta, actually means that x belongs to b a comma delta. Similarly, this condition means that f of x belongs to uh, b f of a comma epsilon. Okay, so maybe this is little confusing. I will just rewrite it. F of a comma f of epsilon. Here also maybe I will change to a comma epsilon. Anyway, they are same. Sorry, a comma x. Okay, right. So here also I should change to f of x. So that means that, so x, so this inequality means that x belongs to b a comma delta. Okay, this inequality means that f of x belongs to epsilon neighborhood of f of a. Okay, okay, so now let's again read the definition of the continuous function. So the definition says that for every epsilon greater than 0, you can find a delta greater than 0 such that if you take a point x belongs to b a comma delta, then its image f of x belongs to b f of a comma epsilon. Okay, so if you, so we can draw the diagram of b a comma delta. So b a comma delta is center at a of radius delta. Okay, so this is delta radius, so this is my circle, and you have to look at all the points inside this circle. Okay, that is what b a comma delta. And similarly, this is my f of a. You take a radius to be epsilon and you draw the circle of radius epsilon, then every point inside this circle is what b f of a comma epsilon. Okay, so there is a very simple definition of continuous function, I mean equivalent definition. So that is basically, if you rewrite that definition, you will get this definition. uh, f is continuous at a if given epsilon greater than 0, there exists delta greater than 0 such that f of b a comma delta contained in b f of a comma epsilon. Basically this means that, so b a comma delta, that means, so if you, okay, so this inequality means that, this inclusion means that if you take x belongs to b of a comma delta, this implies f of x will belongs to b of f of a comma epsilon. That's what this inclusion means. Okay, so we say that f is continuous at a if given epsilon greater than 0, there exists delta greater than 0 such that f of b a comma delta contained in b f of a comma epsilon. Why? So this inclusion actually means that you take a x here and you apply f of x, then f of x belongs to this interval. So in other words, if you take a x here, then that x will satisfy this condition. Then for that x, if you apply f, okay, f will go to the codomain into that f of uh, and that f of x will belongs to epsilon radius epsilon ball center at f of a. In other words, that f of x will satisfy this condition. Okay, so if you can understand this definition, that is much very useful in approaching problems. But this is exactly same as whatever I have written here. Both the definitions are exactly same. Instead of viewing this inequality, viewing it as inequality, I want to view it as a neighborhood. Okay, therefore a function is said to be continuous at a point A. So given a epsilon greater than 0, once you are given a epsilon greater than 0, you draw the epsilon neighborhood of f of A. Then you have to find a delta, you have to find one delta neighborhood of A, such that if you look at the image of this neighborhood under the function f, its image should go inside the uh, epsilon neighborhood of f of a. Okay, so in other words, if you take a x here, its f of x should be lies inside epsilon neighborhood of f of a. Okay, so I hope you this definition is clear. So it is like playing a game. Okay, so suppose I am saying that this function is continuous. Okay, so you can ask, oh, is it? You are saying this function is continuous, is it? Okay, I'll give you a epsilon. Then you have to find a delta. So you will give me a epsilon. Okay, so once you give a epsilon, I want to prove that the function is continuous at this point A. What will I do? First, you gave me epsilon, so that epsilon is arbitrary. You can give me any epsilon. That's why I put for every epsilon. So once you give me an epsilon, I will draw this epsilon radius ball. Okay, so I'll draw this circle of radius epsilon center at f of a, and this is the every point inside this interior is precisely b f of a comma epsilon. Now my task, I say that the function is, I am claiming that this function is continuous at a. So now what I have to do is I have to find one delta neighborhood of a such that the delta neighborhood should be mapped inside this neighborhood, epsilon neighborhood of f of a. So I have to find one such delta. Okay, so this neighborhood is mapped inside this neighborhood, means that if I take any x inside this delta neighborhood of the point A, its image f of x also should go inside the epsilon neighborhood of f of a. Okay, so this is the definition of continuous functions. So given epsilon, you draw the neighborhood here, you have to find a delta here such that the image should go inside. Okay, so now let's see the examples using functions from R to R. So first we make some observation. Okay, so you have given me given a epsilon greater than 0, suppose we have find a delta satisfying 1. Okay, so given a epsilon, what we do, we draw the epsilon neighborhood here. Also we have find a delta such that the delta neighborhood map into the epsilon neighborhood of f of a. Okay, this condition is satisfied. Then we are making some observation. First observation is, if delta works, then any delta 1 less than delta will also work. Okay, that is because if this neighborhood is going inside this neighborhood by the function f, if you draw a smaller neighborhood, so this is delta 1 neighborhood. Okay, so this will also has to go inside this neighborhood, right? Because even if the bigger set is mapped inside the epsilon neighborhood of f of a, then the smaller neighborhood also mapped inside the epsilon neighborhood of f of a. Okay, so that is our first observation. So if for example, if delta equal to 1 works, then delta equal to 1 by 2 will also work for sure. Okay, similarly, if for epsilon, if you got a delta, then the same delta will work for some bigger epsilon also. Okay, why? Because this delta is mapped inside this epsilon neighborhood. Now the epsilon is bigger, epsilon 1 is bigger than epsilon, means now this epsilon 1 neighborhood will be much bigger than epsilon, right? So even the same delta will work for epsilon 1 also, because now for this epsilon 1 I need a delta such that this neighborhood should map inside the epsilon 1 neighborhood, but the same delta which I got for epsilon, if I use, it will go inside epsilon neighborhood f of a by the function f. Okay, therefore the same delta will work for epsilon 1 also, because the epsilon 1 neighborhood of f of a contains epsilon neighborhood of f of a. Okay, so now we come to the functions from R to R. So the domain R, we usually take it as x-axis. Okay, this is my x-axis, my domain, and the codomain real number, field of real numbers, we take in the y-axis. Okay, now, so we just restate the definition for R to R. Okay, so I fix a point A, and I want to find its image. How to find the image of this point A? So I have to go straight to the curve. Okay, so this is, I'll reach this point. This point is A comma f of A. Okay, then if I come here, this point is a f of A. Note that this point, sorry, this point is in domain, this point is in codomain. Okay, so this is my f of a, this is my a. So we say that so this is my graph of the function f. Okay, so we say that this function is continuous at this point a if given epsilon greater than 0. Okay, so once the epsilon is given, what will we do? We draw the epsilon neighborhood in the codomain. Okay, note that here in R2 to R2, epsilon neighborhoods are open disk, everything inside the disk. But in real line, they are just intervals. Okay, so the epsilon neighborhood of f of a is nothing but open interval f of a minus epsilon, comma f of a plus epsilon. This is the epsilon neighborhood of the point f of a. Okay, so I look at, so this is f of a, this is f of a minus epsilon, this is f of a plus epsilon. So to prove this function is continuous, given a epsilon greater than 0, I will draw this epsilon neighborhood around f of a. Now I have to find a delta neighborhood of a. So delta neighborhood of a will be of the form a minus delta comma a plus delta, such that the image of this neighborhood, how to find the image of this neighborhood? So suppose this is my point x. Okay, then to find its image, I have to go towards the curve, then this point will be x comma f of x, then I'll come back here, I'll get f of x. Okay, this is my f of x, this point. Okay, similarly for the whole open neighborhood, I have to go up. Okay, maybe, sorry, so the, maybe I'll draw again. So this whole neighborhood, for every point here, you have to go up. Okay, and you have to come here for every points. Then whatever points you are getting, all those points should lie in the epsilon neighborhood of f of a. Okay, in other words, this neighborhood is mapped inside this epsilon neighborhood. Okay, so that is what we saw here. The delta neighborhood should mapped inside the epsilon neighborhood. So this is delta neighborhood of a, this is epsilon neighborhood of f of a. So these two are very important. Delta neighborhood of a should contained in epsilon neighborhood of f of a. This is what continuity means. Okay. Okay. So now we know the same definition for R to R also. So we prove some functions are continuous, some functions are not continuous using our, so using our this geometric interpretation. Okay. So very first example is constant functions. Okay. We know that constant functions are continuous. Let's see why it is continuous using epsilon delta. Okay. So f from R to R, function is constant for every x. The constant I take it to be c. Okay, so suppose that this c is the this constant. If you look at the graph of the diagram function, it will be like this. Okay, y equal to c. That line is the graph of this function. Now to prove continuity, on I claim that the function is continuous at all the points of R. So I take a arbitrary point a. Okay, and I claim that the function is continuous at this point. So what I have to do, first I have to take a arbitrary epsilon greater than 0. Suppose I am given epsilon, what I have to do, immediately I draw a epsilon neighborhood of the point f of a. Okay, but what is f of a? Every point is mapped to c, so a is also mapped to c, so this c is the f of a. So I have drawn the epsilon neighborhood of f of a. Now I need a delta neighborhood of a such that this delta neighborhood should be mapped inside this epsilon neighborhood. Okay, but if you noticed, this is a constant function. So you take any delta, doesn't matter, very big, very small, whatever. Since the function is a constant function, so whatever delta you take, all these points image will be mapped to this one single point because function is constant, and this point will be always lies inside c minus epsilon comma c plus epsilon. Okay, so whatever delta you choose here, doesn't matter, any delta you can take, yeah, even this much bigger delta also doesn't matter. Its image, if you calculate whatever points you take here, its image will be the single point c. Therefore the image of this interval will be just this point. Okay, so therefore that under this point is belongs to c minus epsilon comma c plus epsilon. Okay, so for constant function you can take any delta, whatever, for given epsilon, if you are given me, if you give me a delta epsilon, I can choose any delta that will satisfy the continuous function criterion. Okay, so given epsilon, you we take any delta. Okay, then if I take x belongs, you take any delta and I take x belongs to a minus delta comma a plus delta, so I take a x here and we want to calculate f of x, so f of x equal to c. Okay, then this f of x is clearly belongs to c minus epsilon comma c plus epsilon because every neighborhood contains at least its center, right? So c belongs to this, therefore f of x belongs to this interval. Okay, therefore whatever x you take here, its image belongs to this interval. Therefore f of a minus delta comma a plus delta contained in f of a minus epsilon comma f of a plus epsilon. This is the delta neighborhood of a, this is the epsilon neighborhood of f of a. Delta neighborhood of a is mapped inside the epsilon neighborhood of f of a, therefore f is continuous. Okay, okay, so same, for the same reason f of x equal to x, the identity function is continuous, but now we have to take delta equal to epsilon. Okay, since the function is mapped to itself, maybe I'll explain this also. So I claim that this is my point a, I claim that the function f is continuous at this point a. So given an epsilon, what I do, first I draw the epsilon neighborhood of f of a. Okay, so if this is a, like a is mapped to itself, so f of a is actually just equal to a. Now maybe these dots may be a little confusing, but yeah, so this is f of a. Okay, now given an epsilon, now I need to find a delta neighborhood of this point a. Okay, a minus delta comma a minus delta comma a plus delta, such that this image should be mapped inside this neighborhood. Okay, but if you look at the graph, every point is mapped to itself, right? So in particular a is also mapped to a only, so this f of a is a. So now I have drawn this neighbor epsilon neighborhood, a plus epsilon, a minus epsilon to a plus epsilon, that is the epsilon neighborhood of f of a equal to a. So I need a delta here such that this delta neighborhood should map inside this epsilon neighborhood, but here you observe that every point is mapped to itself, right? So if I take delta equal to epsilon, so I draw the this delta neighborhood, so this every point in this neighborhood will map to itself. In particular this neighborhood will map to itself only. Okay, therefore if I take delta equal to epsilon, then this neighborhood will be equal to this, yeah, delta neighborhood of a will be equal to epsilon neighborhood of f of a. So if you want this neighborhood to go properly inside this epsilon, you can take delta equal to epsilon by 2. Okay, that will also work, then you will have a smaller neighborhood that will go inside here. Okay, so so for whatever a, we have a delta such that epsilon delta neighborhood of a is mapped inside epsilon neighborhood of f of a, therefore f is continuous. Okay, so we have seen two examples of continuous function. Next we see an example of uh, discontinuous functions, because discontinuous functions are what very interesting. Okay, to understand the definition, discontinuous functions are very interesting. So I define a function from R to R, f of x equal to 2 if x equal to 0 and 1 otherwise. It means that only at the point 0 the function takes the value 2, and all the positive numbers and all the negative numbers the function takes the value 1. Okay, so I hope the function definition is clear. And now we claim that this function is like this function is discontinuous at 0. That is what we are claiming. Okay, you can see that the graph of the function take a jump here. So that is why this function is not continuous. Let's see how to prove this using epsilon and delta. Okay, so let epsilon greater than 0 be given. Okay, so the function is continuous if given epsilon greater than 0, there exists delta greater than 0 such that the delta neighborhood of A should mapped inside epsilon neighborhood of f of A. Okay, so basically, so around 0, if you draw a neighborhood, that will be like minus delta to delta. Okay, this is the delta neighborhood of the point 0. So given a epsilon, okay, so you draw the, so 0 is mapped to 2. Okay, so 2 is the f of 0. So I take a to be 0, f of a is then 2. So given a epsilon neighborhood, given an epsilon, you draw the epsilon neighborhood of f of a. You need to find a delta here such that this delta neighborhood is mapped inside this epsilon neighborhood if f is continuous. Okay, but if to prove f is not continuous, what we have to do is, maybe again we go back to the R2 to R2 definition. So a function is continuous if whatever epsilon neighborhood you draw about f of a, you can draw a neighborhood, you can draw a delta neighborhood such that this neighborhood mapped inside this neighborhood. Okay, so here for every, okay, for every epsilon greater than 0, you have to find one delta such that this happens. But now to prove not continuous, you have to find one epsilon. Okay, such that you have to find one epsilon neighborhood of f of a such that whatever delta neighborhood you draw, bigger, smaller, doesn't matter, whatever delta neighborhood you draw about a, that delta neighborhood image should not go inside the epsilon neighborhood of f of a. Okay, okay, if f is continuous, then for every epsilon you can find one delta such that this thing happens. Okay, so to prove some function is not continuous, yeah, you have to find one epsilon such that whatever delta neighborhood you take of the point A, its image will not go inside the epsilon neighborhood of f of A. Okay, so that is the uh, that is the that is what means to say function is discontinuous at the point A. Okay, so try to understand it, then it will be very easy. Okay, now let's go back to our example. So to prove function is not continuous, we want to prove that there is a one epsilon such that for every delta, this uh, delta neighborhood of A is not mapped inside epsilon neighborhood of f of a. Okay, note that f of a is 2. If I take a to be 0, then f of a is 2 in this function. So this is what we want. So what epsilon? So we can take, we have to find one epsilon such that for every delta this happen. Okay, so what is that epsilon? That is the question. Okay, so let's come back to the diagram. We want to find one epsilon neighborhood of this point delta such that whatever delta neighborhood you draw for the function for the point 0, its image should not go inside the epsilon neighborhood of the point 2. Okay, now if you noticed, the image has only 2 points. One is 2, another is 1. So every point is either mapped to 1 or 2. Okay, so if I draw this neighborhood, like the neighborhood of radius half, so basically I take epsilon equal to half, then that neighborhood will be open interval 1.5 to open interval 2.5. Okay, so this is my epsilon. Now if I take any delta neighborhood of 0, any delta neighborhood of 0 will have positive points as well as negative points. Okay, so all those points will map to 1 also. So for every delta, minus delta comma delta contains both 1 and 2, because this neighborhood contains 0. Therefore f of that neighborhood will contains 2. This neighborhood contains a non-zero number also, so therefore f of that neighborhood will contains 1 also. So f of minus delta comma delta is equal to 1 comma 2. Okay, so if I draw a epsilon neighborhood such that that contains only the point 2, then definitely image of this delta neighborhood around 0 cannot be subset of uh, this epsilon neighborhood of 2 or f of 0. This 1 comma 2, note that 1 comma 2 is not a subset of 1.5 comma 2.5, correct? Therefore we conclude that if you take epsilon equal to half, so if you take epsilon equal to half for every delta, this image of the delta neighborhood of 0, that will be 1 comma 2. That 1 comma 2 will not contained in open interval 1.5 comma 2.5. This is the epsilon neighborhood of f of 0, which is 2. Okay, therefore there is a epsilon greater than 0, that is which is equal to half in this case, such that for every delta f of b0 comma delta not contained in b2 comma epsilon. Okay, therefore the function is not continuous at the point 0. Okay, okay guys, so let me stop here. This is the end of the lecture 1 on continuous functions. You try to revisit it and you try to understand this definition properly. Tomorrow we'll see more examples and we see the other definition of continuous functions also, limit definitions, and the inverse image of open set is open, inverse image of closed set is closed, that definition also, and sequence criterion. All these things we will see tomorrow. Okay, and if you learned something new from this video, please click the like button and share with your friends also, and subscribe to my channel. Thank you.